All right, so we'll look at one more example here, this one involving a pendulum, and we're going to figure out the maximum speed. In this case, we're looking for the maximum speed of the end of the pendulum, the 750 gram bob at the end of the pendulum. So we've got a 1.2 meter pendulum, it's pulled at 10 degrees to the side and released, and we want to know what is the maximum speed. So when we're talking about pendulums like this, the tricky part, and that line is pretty thick, let's make it a little bit thinner here. So obviously we've got a pendulum. If it was hanging straight up and down at its equilibrium point, this is the point where its speed is going to be the maximum. So imagine we have pulled this to the side. And we've pulled it to the side 10 degrees. This is 1.2 meters. And we've let it go. And we want to know what is the maximum speed. So the maximum speed is going to happen as it passes through this equilibrium point here. So let's write down what we know. Mass, 750 grams equals 0.750 kilograms. We know the length of the pendulum is 1.2 meters. And we know the angle is 10 degrees. So we don't know a ton of information here. Just like all of these energy questions, our energy at the start has to be equal to the energy at the end. When we're at the start, when it's pulled to the side, this is sort of our starting situation, we only have potential energy. And this is the potential energy of gravity, because the object isn't moving, there's no springs involved. The only type of energy we have is the potential energy of gravity. And this is going to be equal to, we'll write it as the kinetic energy of the bob at the bottom. And so the amount of potential energy that we have at the start, as always, is going to be the mass multiplied by the acceleration of gravity multiplied by the height. And this is the tricky part, is what is the height? How far does the pendulum start above where it ends up? So if I was to draw this height on my diagram here, the height here is this length right there, right? So the height is the difference between where it starts and where it ends up. And if we want to figure out what this height is, well, we're going to have to do a little bit of trigonometry here. So if we think about this 1.2 meters is the entire length of this side. When the pendulum has moved to the side, didn't want that to happen. Right. Of course, this is also 1.2 meters because the length of the pendulum isn't changing. So really what we have to figure out is when the pendulum has moved to the side, what is the distance, the vertical distance here? We'll call it dy maybe. What is this vertical distance? Because we can say that the height here plus that vertical distance are going to be equal to this total length, right? Hopefully that makes sense. So we've got this total distance here all the way from when the pendulum is in its vertical position is 1.2 meters. And that is the combination of the change in height plus the vertical part of this pendulum when it is to the side. So we need to figure out what this vertical height is. So really, let me draw this off to the side here. We've got a triangle here with 1.2 meters on that side, and this is what we're trying to figure out is the height. 10 degrees there. So we can use cosine of 10 degrees is going to be equal to our adjacent side divided by 1.2 meters. This vertical side is going to be equal to 1.2 times cosine of 10 is going to be equal to, this is going to be very close to 1.2. It's 1.182 meters.
So we can plug that in here, and we can say that our height is going to be equal to 1.2 meters minus dy, 1.2 meters minus 1.182 meters. So the change in the height from when the pendulum is pulled to the side to when it gets down to the bottom is actually not going to be a very big number. 0.01823 meters. So that's what this height is here between the place that the pendulum starts and the place that the pendulum ends. So that's the potential energy that we're going to be dealing with. So getting back to where we were, we said that we had potential energy due to gravity at the start was going to be equal to our kinetic energy at the end. And we said this was equal to mgh is equal to 1/2 mv squared. And we're trying to figure out the velocity again. So again, here we're going to have to cancel out the masses. So gh equals 1/2 v squared. Multiply both sides by 2. Just going to cancel out the 1/2. And then we'll square root both sides. So the square root of 2gh is going to be equal to our speed. So square root of 2 times 9.81 meters per second squared multiplied by that height that we had, which was that 0.01823 meters, should be equal to our speed. So if we multiply this out, we get that the speed of the pendulum at the bottom is 0.60 meters per second. So again, we used conservation of energy to figure out how fast the pendulum is going at the bottom. I think the hardest part of this one is doing this trigonometry where we're trying to figure out what's going on with the height. And so it's important to keep that in mind, is that the height is the difference between the total height of the pendulum when it's straight up and down versus when it's to the side. And then it's just a matter of using conservation of energy, where our energy at the start is going to be equal to our energy at the end.